Let x be a continuous random variable with probability density function fxx, and suppose y is equal to gx is strictly monotonic, either increasing or decreasing function of x, and also assume that gx is a differentiable function for x. So then we can directly find the probability density function of y from the probability density function of x by this formula. So let us discuss this. What are the conditions? So let x be a continuous, so x be a continuous random variable with probability density function fxx and g R2 are strictly increasing and differentiable function. So G R2 are strictly increasing and differentiable function. So it is strictly monotonic actually. So we can write strictly increasing or decreasing. So basically it is not constant anywhere, decreasing function. So suppose if it is strictly increasing, so strictly means, so x1 is less than x2. If x1 is less than x2, either gx1 will be less than gx of x2, so strictly increasing, or gx1 will be strictly greater than gx2. So basically it will not be less than equal to. Usually we say that it is increasing function means x1 is less than x2 implies gx1 is less than equal to gx2. Or decreasing function means if x1 is less than x2, then gx1 is greater than equal to gx2. But it is strictly, that's why gx1 has to be strictly greater than gx2. So in that case actually this derivative, if you take the derivative, so suppose y is equal to gx, so then this inverse exists. So with this condition the inverse will exist, and the inverse of g of c is denoted as h. So h is equal to g inverse. So that means x is equal to g inverse of y. So if you, so g inverse of y, which is equal to h of y. Now if you find the dx of dy, so this will be dh of y by dy. So dy of hy, so dx dy. So it will be either greater than 0 or less than 0. It will not be like for all y. So for all y belongs to the real number. So because it is strictly increasing or strictly decreasing, so it will not be equal to 0 anywhere. So it will be either greater than 0 for all y belongs to R, or it will be less than 0 for all y belongs to R. So in that case, so the probability density function of y can be found is given by, so by this relationship f of y will be, so because this dx dy, it is either greater than 0 or less than 0, we just take this absolute values of this value dx dy, whatever the value, it will be the positive value we will consider for all y, whatever it will come, it will take the absolute value into fx of x is nothing but h of y. So this is x is h of y. So this will be a function of y. So this probability density function f of y can be found using the probability density function of x in this relationship. So this is the theorem it is given. So before going to prove this theorem, let us discuss this numerical example. Let us see this numerical example. So whatever we have considered this previous example, so here, so you can see that it is very lengthy process. Find first, suppose this is the probability density function and this is the transformation. You first find the cumulative distribution function and then find the cumulative distribution function of y, and then you take the derivative, and then you find the cumulative distribution probability density function of y. So here we will use this theorem directly from PDF probability density function of x, we will directly find the probability density function of y. Let x be a continuous random variable with the probability density function of x given by f of xx is equal to, it is 2x, whenever x is between 0 and 1 it will be 0 otherwise. So find the probability density function of y is equal to gx, this is equal to 3x plus 1. So that is the previous problem we discussed. So using usual general method, y equal to 3x plus 1. So here you can see that this transformation y is equal to gx, this is 3x plus 1 is strictly increasing function, and also the inverse, how we can find the inverse, x 3x is equal to 3x plus 1 will be is equal to y, and which implies x 3x is equal to y minus 1 implies x is y minus 1 by 3. So this is the h of y. So this is x is equal to h of y. So this is the inverse of the function y, x is equal to g inverse y, this is y minus 1 by 3. So what will be the dx dy? So dx dy will be nothing but, since 1 by 3 it is always greater than 0 for I belongs to the real number. So since it is always greater than 0, it is a strictly increasing function. So the probability density function, of y is given by f of y. So this is this absolute value of dx dy into f of x of h of y. So this is the formula, we have already discussed this theorem. So this is the f of x h y dx dy. So now dx dy is 1 by 3. So this is 1 by 3 into fx of hy. So fx of hy actually nothing but fx of, what is hy? Hy is g inverse of y, this is y minus 1 by 3. This is y minus 1 by 3. So then this fx x here y minus 1 by 3 will write here. So this is equal to 2x, 2 into y minus 1 by 3 by 1 by 3 is there on already 1 by 3. Let us write down it. So this is equal to here, suppose. So this is equal to 1 by 3 is there, and then fx of y minus 1 by 3, this is 2 into x. So into 2 into x is y minus 1 by 3, y minus 1 by 3. Whenever y minus 1 by 3 is less than 1, greater than 0, this is 0 otherwise. So now if you simplify these things, what we get? So it is 9, 2 by 9 y minus 1, if y, if you multiply by 3, this is 3, 0, and then add 1. So 1 less than y less than 3 plus 1, 4, it is 0 otherwise. Because it is continuous random variable, we can write any either strictly inequality, because at a point probability is 0, it will not change if you find the probability of an interval. If you do the integration, so this value will not change with this, if you consider either strictly less than or only less than equal to, like that. So 2 by 9 y minus 1, if y is greater than 1 less than equal to 4, because or you can write this also, but this does not change. But if you find, you can see that we also got the same 2 by 9 1 by minus 1, but this process was complicated. Here we just using this theorem we directly found this value. So this is very simple now. Now we can use this method for finding probability density function for any other random variables also, transformation of random variable, if this condition satisfies. So let us discuss another example. So let y is equal to 10x, find the probability density function of y if x is a uniform random variable over 0 to 1. So let us consider that. let, so x is uniform random variable 0 to 1. Hence, the probability density function of x is given by, so f of xx is equal to 1 if x is greater than 0, less than 1, it is 0 otherwise. So, this is the let us see that problem. X is uniform 0 1, so this is the density function, and then you take the transformation yx. The transformation y is equal to gx here. This is nothing but tan x. So, tan x is a strictly increasing function between 0 to 1. So, if you consider y is equal to tan of x, so then x is equal to tan inverse of y. So, whenever x between 0 to 1, so this is, I think it will be complicated. I think this numerical example has some typo. So, it is asked that it is uniform distribution on 0 to pi by 2. So, this is pi by 2. So, that is why, because we know that tan is increasing in 0 to pi by 2. So, now this is pi by 2 minus 1. So, this is 1 by b minus a, this is, so this is pi by 2. So, let us consider again, let x is a uniform random variable between on 0 to pi by 2, then the probability density function of x is given by 2 by pi if x between 0 to pi by 2, it is 0 otherwise. So, the reason is that you can consider it, but this form will be very not very standard form, whatever we will finally found, it will be a complicated form. Otherwise, it is also increasing in 0 to 1, so it could be done. So, now x is y is, so tan inverse of y, so it is an increasing function. So, now what will be the dx dy? So, dx dy will be 1 by 1 plus y square. So, derivative of, so we know that derivative of tan inverse y is 1 by 1 plus y square, and this is always greater than 0 for any values of y. So, note that whenever minimum value of x is 0, so y is 0, and maximum value x is pi by 2. So, whenever x goes to pi by 2, then y goes to infinity, because so y is actually between 0 to infinity. For y is less than 0, then this density does not exist. So, now for y belongs to 0 to infinity, this is always greater than 0. For any real number, actually this is also greater than 0. Now, how we can find the probability density function of y? Now, we will use this formula. So, x is equal to tan inverse y, this is the hy now. Now, hence the probability density function, hence the probability density function of y is given by f of y, this is equal to, by we will use this formula, absolute values of dx dy and into fx of hy. So, fx of hy. So, this is 1 by dx dy. So, this is always positive. So, this is be 1 plus 1 by y square, 1 plus y square into fx of hy. Fx of hy is fx of tan inverse of y. Fx of tan inverse of y. So, hy is tan inverse of y. Now, what is fx? Fx function is given by here. Fx is here. So, then we can write here. So, see that whenever x between 0 to pi by 2, so x between 0 to pi by 2 means tan inverse y between 0 to pi by 2. If tan inverse of y between pi by 2 and greater than 0, so then the fx of this value will be 2 by pi, it will be 2 by pi, and also this quantity is there 1 plus y square, 1 plus y square. Otherwise, this value will be is equal to 0, 0 otherwise. So this is, it is coming like that, 2 by pi 1 plus y square. So now this interval we can simplify by because tan is an increasing function, so this can be represented as next line. So hence the probability density function of y is given by f of y is equal to, so this is equal to 2 by pi 1 plus y square if you, then this is if you, tan is increasing function, so 0 tan 0 0, this is y, and whenever it is pi by 2, tan pi by 2, it is goes to infinity if y is between 0 to infinity, and this is equal to 0 otherwise. Okay, so this is the okay, so hopefully you have followed this. So this is how we can find this probability transformation of random variable. Now what we are using this theorem, let us see how this theorem actually it is true or false. We want to prove this theorem. Let us prove this theorem. So this theorem says that, so without loss of generality, without loss of generality, so let us assume that, so we just let us write that this way, without loss of generality. Let us assume that basically we want to say that G R to R here either strictly increasing or decreasing. So let G R to R be strictly increasing. So for decreasing function it will be similarly it is done. Let G R to R be strictly increasing function. So now and so let and x be a continuous random variable with the probability density function of x is fxx, probability density function is fxx, and cumulative distribution function of x is capital Fxx. Okay. So now why the cumulative distribution function of y is equal to gx is given by, so f of y, this is probability that y less than equal to y. So that is nothing but probability that y is gx less than equal to small y. Now since this is a strictly increasing function and g inverse also exists in our assumption that because it is a strictly increasing function and differentiable also, so if we both side if we use g inverse, so this is nothing but x is less than equal to g inverse of y. So g inverse of y we denoted as hy, x is less than equal to hy. So hence it is nothing but f of x of hy, f of x of hy. Hence from here we can get that, hence the probability density function of y is given by, so probability density function will be capital small fyy. It is nothing but differentiation with respect to the cumulative distribution of f of yy. So it is nothing but differentiation with respect to fx of hy. So by composite function we first differentiate with respect to x. So that means it is nothing but d of hy dy. So it is ddx of, so basically f of x ddx of f of x evaluated at, so let us write down in the next page. So what we found, fyy we found is f of x hy. Now we differentiate and we get the probability density function PDF, which implies ddy of f of y. So then it is nothing but d of y, sorry, ddy of fx of hy. So that can be represented by dx dy into ddx of fx x evaluated at x is equal to hy. So that is so x is nothing but dhy dy and ddx of fxs is nothing but capital small xx evaluated at hy is hy. So that we found it. Now if it is decreasing, so if g r2r is strictly decreasing function, so if g r2r strictly decreasing function, so then the CDF we can find the cumulative distribution function of y is fyy. So that is nothing but probability that y less than equal to y. So probability that y is gx, gx less than equal to y. Now because it is strictly decreasing function, this probability will be same as x greater than equal to g inverse of y, because it is strictly decreasing function. So this is can be represented as, so now first we can, so this is because it is a continuous random variable, it is nothing but probability that x less than minus probability of x of, so g inverse y. So this is probability of x greater than hy. So because continuous, so you can write equal to or maybe, so that x less than equal to hy, this is same at a point this probability is 0. So this is less than equal to hy. So then this what we found, this is nothing but 1 minus fx of hy. So whatever we found here it is nothing but 1 minus of this. So hence the probability density function of y is given by f of capital small f of y. So this is derivative with respect to y of f of y. So this is derivative with respect to y. So here you can see that 1 minus fx of hy. So it is same as minus of ddy of fx of hy. So what we found that it is nothing but minus of dhy dy fx of hy. Now for whenever it is decreasing, so this is negative, this value is negative, so that's why minus of this it will be again a positive value. So that's why both the cases if you combined for strictly increasing and decreasing, we can combinedly write that, hence we can combinedly write from 1 and hence from 1 and 2 we have f of y is, so because for increasing case it is dhy dy, this is positive, for decreasing case this is negative, again minus of this it will be positive again. So this is fx of hy. So both the case if you consider, this is the theorem. So note that this theorem it will be applicable whenever x is a continuous random variable, we are taking a transformation y is equal to gx, which is strictly increasing or decreasing function, and also it is differentiable, and hence a inverse also exists. So this is this, I think you have followed this result. So another example, let us do this example. X is normal distribution with mean 0 and variance 1, and y is equal to e to the power of x. Find the probability density function of y. Let us apply this theorem again. So let x is normal distribution mean 0 variance ones. The probability density function, find the probability density function of y is equal to e to the power x, where x is normal distribution with mean 0 and variance 1. Let x is normal distribution, mean 0 and variance 1, then the probability density function of x is given by f of x is equal to 1 by root 2 pi e to the power of minus x square by 2, because it is sigma is 1, x is mu is 0, x is minus infinity to plus infinity. So then what is the transformation? Transformation is PDF of y is e to the power of x. So let us consider y is equal to e to the power of x. So this is gx, g of x, this is e to the power of x. So this is the transformation it is considered, y is equal to e to the power of x. So g is a function from R to R, and g of x is, so consider that e to the power of x. So this is y is equal to g of x, so e to the power of x. So it is a strictly increasing function because it is exponential function, random variable. Now what is the inverse of x? So x is nothing but log of y. So it is the inverse of x denoted by g of y. So this is g inverse of h of y, sorry, h of y is denoted as g inverse of y. So now what is dx dy? So dx dy, or the dy hy dy actually, dx dy, this is 1 by y. So now this is 1 by y. Now note that whenever you are taking this transformation e to the power of x, so this y is always, this is greater than 0. Hence 1 by y will be greater than 0 for all y in the range of this random variable. So between 0 to 1. So because for this transformation x initially it is minus infinity to plus infinity, but whenever you are taking this transformation y, the range of y become 0 to 1. So that's why in this region of this transformation y, so it is actually greater than 0. So it is a strictly increasing function also, and then hence the probability density function of y is, probability density function of y is given by f of y, this is equal to by dx dy. So note that x is here hy, so dhy dy sometimes we are writing in this notation. So this is same as dx dy actually, x is equal to hy. So that's why we are writing in this way. So but the notation is, we understand the same, into fx of hy. So this is 1 by y. Now fx of hy is what? 1 by root 2 pi, 1 by root 2 pi e to the power of minus okay, let us write another line, dx dy into fx of hy is here, hy is log of y, log of y. So 1 by y root over root 2 pi e to the power of minus log y of whole square, x is log y, h of y log y whole square by 2. So whenever y is greater than 0, less than infinity, because x is minus infinity to plus infinity, but here hy has to be minus infinity plus infinity. Hy is nothing but hy is log y. So log y is between minus infinity to plus infinity, it is same as y is between 0 to infinity. So let us write down. So log y is between plus minus infinity to plus infinity. Now because it is a e to the power transformation, if you so same, so this is now which is 0 any other cases, 0 any other values of y otherwise. So this can be simplified by, so 1 by root 2 pi, 1 by root 2 pi y e to the power of minus log y whole square by 2 whenever. So now if we multiply, so if you this interval does not change, inequality does not change. If you apply this strictly increasing function e to the power of, so exponential, so it will be minus. So if you take the e to the power minus infinity means it is 0 greater than less than 0, and this is y, and then this is infinitive, this will be 0 otherwise, this is 0 otherwise. So this is some of the numerical example we work out here, and this is the concept of transformation of random variable in univariate cases. So hopefully you have followed that, and you can go through some more examples, some of the references you will find more numerical examples. So also you can go through whether all the computations are correct, otherwise you can see that, you can check what are the correct expressions here, and you can see more reference books, it is given in the beginning we discussed. So those reference books you will find more numerical examples, some of the you will ask in the assignments also, you will find in the assignments also some of the problems, and then you will be you can practice it, and then if you have any doubt you can again clarify it, you can practice, then you can, it will be very much clear. So this is the concept of transformation of random variable and the corresponding numerical examples for the univariate random variable cases. For the more than one random variable, suppose bivariate random variable or multivariate random variable, next we will discuss how this transformation of random variable we can deal, or what are the related theorems, results, and some of the numerical examples we will study.